We're going to do moments, and moments is a turning force. Okay, so it's a turning force. Right, first of all, recall that a force can be cause an object to turn or rotate. So let's have a look at this turn or rotate. You see that? Turn and rotate. Force can use an object to turn around a pivot. Here is our pivot. Okay, let's go back and show this again. Okay, and there you have your turning force. Okay, so it goes about a pivot, sometimes called a fulcrum as well. Okay, and what we need to do is to calculate that moment, that turning force. Okay, we need to know the distance from the pivot and the force which is being applied. Okay, so this moment, okay, is that force to turn. For example, if you're using a spanner, if you've opened a door and you open the door like this, a turning force. Okay, or if you've ever balanced an object, okay, you'll be familiar with moments. Now, it's difficult to tighten it with your fingers. Okay, it's easy with a spanner, and that's because the further away from the pivot you have, the higher the moment will be, and we'll show you why that is when we do the calculation. The turning effect of the force is called the moment, okay, and you use this equation to do it. So the moment is equal to the force times the perpendicular distance from the pivot point. So basically that means the distance between the pivot point here and where the hand is joined on here. And usually go to the middle of the object if that's the case, okay? And you can see the distance here. So basically it's the distance times the force. And we usually go distance, again, in meters and the force in newtons. So the unit of the moment is Newton meters, because Newton times meters. So Newton meters. Okay, and that tells you what the units are for each. Now moments require the amount of force in a perpendicular right angle direction. So if we look at these, you can see that this is at a right angle to where the turning force should be applied. So you see here and then down, right? And then this is not, and this is not, so the biggest turning effect is going to be this one here. Okay, so let's take the two away and then let's look at some examples. So we're going to look at them here, a bit bigger. So if we look here, what we could do, 3 times 4. So 3 times 4 is 12 Newton meters. And that's as simple as moments are. Moments are just taking the distance between the pivot here and here, and then the force that's applied, 3 times 4 is 12. Okay, so we have the next one. 3 times 2 is 6. Okay, and then we look at this one. Now, this is a slightly weird one because it has to be at right angles to the force. So we don't measure it here, we measure it here. Can you see it has to be at right angles? So therefore 3 times 2 is 6 Newton meters. So 3 examples of how you calculate simple moments. Now moments have a direction and they're described as clockwise or anti-clockwise. The direction of a moment is determined by which way the force is trying to rotate it. So I'm going clockwise here, I'm going anti-clockwise here, and you can see they're the two versions of the force. If you're not sure about clockwise and anti-clockwise, it's the way in which the clock goes. So if the clock goes that way, it's clockwise. If it goes this way, it's anti-clockwise. Okay? Right, if an object is in equilibrium, okay, balanced, then the forces on a body must be balanced, and that includes turning forces. So we're going to go through an example of this. If an object is in equilibrium, the sum of the moments is equal to the sum of the anti-clockwise moments. So if I go and look at the clockwise moments and I look at the anti-clockwise moments, if they're equal, there's going to be no turning involved. Okay? So let's have a look at this slightly complicated example. I'm going to go through 2 examples. So here we have this object here is 2 meters away from the pivot and there's 10 newtons. So 2 times 10 is 20. And that is going in this direction, therefore it's anti-clockwise. So anti-clockwise 20 Newton meters. If we look at this one, 8, okay, and it's 1 meter away. See that? So 8 times 1 is the first clockwise moment. And then this one is at 4 times 3. 4 times 3 is 12. Okay, so that's 12 plus 8, which is 20. So you add the moments together if they're on the same side of the pivot and going in the same direction. That means 20 plus 20 is 40, which this means this is in equilibrium and it is balanced. Let's look at another one, and you can see here 2 meters from the pivot, 10, 2 times 10 is 20. If we look here, 4 meters away from the pivot, 5 times 4 is 20. Okay, so we've got 5 times 4 is 20 and 10 times 2 is 20. So again, this is balanced. Okay, now that's some examples of moments and calculating simple moments and being able to tell whether something is in equilibrium or not.